Hello everyone, my name is Wang. I'm a PhD student from the University of Tennessee. I'll present our work channel pruning via Lookahead search-guided reinforcement learning. In recent years, deep neural networks have been widely used in different computer vision applications. However, the computing cost in these CNNs is usually expensive, which constrain their usage on resource-limited devices such as robotics and phones. Network pruning is one of the most popular approaches for neural network acceleration. Network pruning aims to compress a deep neural network by removing unimportant filters while maintaining its performance. Although it is very successful, most of existing channel pruning approaches are faced with the following two issues. First of all, filters importance heavily relies on the fast estimation of filter importance while sacrificing some ranking precision. Second, filters are often pruned with a greedy selection strategy without a look-ahead mechanism. With the above concerns, we propose a novel channel pruning approach with look-ahead search-guided reinforcement learning. We train a neural network with reinforcement learning that learns to prune a sequence of filters and maximize the performance of the slim network. We also implemented a look-ahead mechanism with Monte Carlo tree search, which can improve the sample efficiency of the RL training process. Given a CNN to be pruned, our policy network takes a number of filter-related features as the input and output the probabilities of pruning each filter. The input includes silence responses, such as mean activation value of each filter, and filter weights, and the structure-related quantities, such as how many filters exist in each convolutional layer. After a filter is pruned based on the output probabilities, a slim CNN architecture is obtained, whose features are used as the input in the next iteration. For each intermediate CNN during the pruning process, before the filter selection, a Monte Carlo tree search is executed to provide a look-ahead search and generate much stronger policies for RL training. To establish a search tree, we consider each intermediate CNN structure as a node. A directed edge exists from node A to B if B is obtained by removing a filter from A. For each node in the tree, we maintain the following three quantities: the expected reward for action A from state S, the number of times that an action A is selected from state S, and the prior probabilities of pruning filters from the policy network. Starting with a CNN to be pruned and an empty tree, the MCTS is iteratively executed by selecting actions that maximize the upper confidence bound. When a leaf node is reached by continuously expanding nodes for all traverse edges, the associated values stored in the search tree are updated. After the MCTS search, the improved policy pi can be simply obtained by normalizing the visited count NSA. We evaluate our approach with several benchmark networks and datasets. With the Net5 and MNIST, our approach prunes 95% of the total flops, and the test accuracy can still increase to 99.28% after fine-tuning. The previous best performance is only 99.18% by pruning 71 flops. We also conduct experiments of pruning VGG16 and ResNet56 on CIFAR10. Our approach can reduce nearly 80% of the total flops on VGG16 with no performance loss. On ResNet56, our prune model also outperforms other approach. Finally, we present the results of ResNet 50 on the large-scale dataset ImageNet. Similarly, by pruning nearly half of the flops, the network's top 1, top 5 accuracies only drop slightly. We also conduct several ablation studies to validate the effectiveness of the proposed approach. It can be observed that with more training iterations or MCTS executions, the performance can be improved. Thank you for watching.